Okay, hello, welcome back. So in the previous video, we saw how we can take derivative of a vector in a fixed or in a rotating frame. Now let's use that kind of information to find the positions, velocities, and accelerations in a bunch of famous frames. So the most basic one everybody is familiar with is the Cartesian frame, where we have this orthonormal XYZ reference frame. We have a particle at position that is described by the vector r. So what we can do is project like this. Project this vector onto the three axes. This is x, this is y, and this is z. So in this case, my vector r, the position is xi plus y, yj plus zk. Now the velocity v is the derivative of that, but Cartesian frame, usually we, at least in this case, we consider it fixed. So it's going to be only x dot I plus y dot j plus z dot k. Essentially, the velocities along each axis gives us the velocity vector, and likewise the acceleration is x double dot I plus y double dot j plus z double dot k. So this is the case for position, velocities, and accelerations in a fixed Cartesian frame. The next very useful one is a cylindrical, what is called a cylindrical frame. And let me change colors. Green. Green is my favorite. So what we have in this cylindrical frame, sorry, it's a little difficult to do dotted lines on this. Okay. So I can, maybe let's go a little bit further. That's not the best projection, but it's all right. So we have this projection. Let's call this length r, and that angle phi. So take a note that this r and that length are actually different. So in this, where is my? I can create another reference frame. This one I call ER. This is really difficult. And pay more. It's difficult. So I'm using a drawing tablet. It gets some used to. This is EZ. And I'm going to define a third vector in the direction of increasing theta and perpendicular to r. So it is still this E phi is in the same plane as this xy plane, but it is perpendicular to ER, and all three of them are now perpendicular. So with the definition of r being the length of this projection, what I can do is my r position vector, I can write it along the three axes. There is no component along the phi axis. So I have essentially this vector plus that one. So I have r ER plus z. Z is this projection. This is Z. Z, Ez. So that is the position vector. The velocity is derivative of that. So I have so here's a good one, good example of good use case of what we saw in the previous video. Now as my particle just moves around, this frame rotates about z-axis and follows and points toward the location of R, or more specifically toward this projection of R. So we are dealing with a rotating frame. So derivative of R, let's maybe write it like this: R dot equals V. We saw that it is R dot relative as measured from the perspective of an observer that also rotates with this frame, plus omega, the rate of change or rate of rotation of the frame cross R. So in this case, omega, the vector omega is the frame is rotating about z, so it is in k direction, and the rate is phi dot, or no, not k, let's call it Ez. And what else can we write? So this R dot, the relative position. So if I sit on this frame that rotates and I just observe how much the component of these components R and Z change, so that is R dot ER plus Z dot EZ. That is the relative one. Plus, now I have omega phi dot Ez cross my R, which is RER plus ZEZ. And if you work out the cross product and gather the terms, you will have R dot, what is it? R dot ER, oops, R dot ER plus R phi dot E phi plus Z dot Ez. So this is the velocity in cylindrical, or sometimes only if you're looking at the 2D, it's called a polar frame without the Z component. So R dot is the rate of change of lengths along basically along the rate of change of this length. R phi dot is the more or less tangential component, and Z dot is the rate of change in the vertical direction. And finally, I can work out the acceleration, which is V dot. V dot equals A. I can take derivative of this. So I have R double dot ER plus R dot ER dot plus derivative of this. I have three things now. R dot phi dot E phi plus R phi double dot E phi plus R phi dot E phi dot plus Z double dot EZ plus Z dot E dot Z. And you can, for this one and for that one, you can follow the same procedure as before. This one is 0 because my frame is rotating about z, so z doesn't change actually. And if you work out the details, you'll end up with r double dot minus r phi dot squared er. This is the acceleration along r, plus r phi double dot plus 2r dot phi dot. This is the component of e phi plus z double dot ez. And this is the acceleration. Oof. Where is my control Z? Do I have undo here? No. Okay. And this term more or less represents the centripetal acceleration. This one is a tangential acceleration due to accelerating rate of accelerating rotation. And this is a combined effect of both as the length changes and as the frame rotates. And the component along z remain more or less simple. All right, so the next one is a spherical frame. Now this one is a little different. This one. So before we had this projection, let me try to do it again. This is rather difficult. Okay, this is projection. Oh, not the right direction. Okay. We still call this angle phi, but instead of looking at this projection, I'm going to work with this direction of r itself and then call this angle theta. This is the spherical frame described by one length and two angles that fully describe the position of my particle. So similar to before, now I'm going to define a coordinate frame. So this time I'm going to directly point toward my particle and call that ER. Now I'm going to define a vector in the direction of rotation of phi and perpendicular to this ER. So this is going to be my E phi. So these two are perpendicular. It's still on the same plane. This E phi is on the XY plane. And this is also perpendicular to that. And the last one is the E theta. In this case, it's going to point down a little behind the page. This is E theta. And all of these are perpendicular to each other. So as this goes down, this E theta rotates inward and remains perpendicular to the line, and it is in this plane. So in this projection plane, that is where this E theta lies. So again, as particle moves around, I have this frame ER, E phi, E theta following it and rotating. So it is a good idea to try to figure out what the angular velocity of that frame is. So what I have is this phi dot as it changes. I have this phi dot. There is a component of rotation about the z-axis. So this is phi dot k. And there is also a component as theta increases. I have theta dot. The rotation is about this e phi axis. This is the true angular velocity of the frame, but I have this k. I don't like that. I want to transform that or write it also in terms of my existing er, e phi, e theta. So this phi dot k is some kind of axis along the vertical, my z-axis, and I can write or project that onto the rest of my coordinate frames. There is not going to be any e phi because that is out of this plane. I will have some er and e theta components. So that is going to be phi dot. My k is cosine of theta because it's unit length. Cosine of theta er. That is a component along the r axis plus sine of theta e. What is it? E theta. And I still have the theta dot e phi. So that is the angular velocity that we can work with. Okay, going back to the definitions, I have my position vector here very conveniently defined as r, the length of this vector, times er. And notice the difference of the definition of this length r here compared to the previous in cylindrical frame. These are different definitions. Now I have v. I can define v. V is sometimes my pen goes unresponsive. I don't know. Come on, you can do it. So again, this is a derivative. This is r dot, a derivative of a vector in a rotating frame. So I have this r dot relative plus omega cross r. And I have the omega, I have r, and this term, the relative, as the observer looks at this point and moves around, the observer sits on the r phi theta frame, it only sees r dot, the rate of change of this length only, er. Plus this omega cross r, so let's write it phi dot cosine of theta er plus theta dot e phi plus sine of theta, phi dot sine of theta, what did you have, e theta, times or cross my r, which is r. If you work out this cross product is going to be a little lengthy. So what I have is r, let me see if I don't miss any term. I have r dot er plus r theta dot e theta plus r phi dot sine of theta e phi. So this is a velocity in terms of r dot, theta dot, and phi dot. And next one is acceleration. I can take derivative of this and follow the same procedure. What I'll end up with is a quite lengthy formula, r double dot minus r theta dot squared minus r phi dot squared sine squared of theta, that is the radial component, plus r theta double dot plus 2r dot theta dot minus r phi dot squared sine of theta, sine of theta cosine of theta e theta, and the last one r phi double dot sine of theta plus 2r dot theta dot sine of theta plus 2r theta dot phi dot cosine of theta. This is E phi component. Okay, quite lengthy, nonetheless useful. That if it is useful in conditions that we especially have a spherical rotation, and we can calculate the position velocities and accelerations knowing the rate of change of these angles and the lengths. Okay, the last one is very common when we know the path of the particle, and we can create a frame normal and tangential to that path. So let's see. If we know the path of the particle, we can define one vector tangential to that path. Let's call it ET, and one momentarily normal to the path. So it's going to be something like this. Call it EN. And we can create a third one that is normal to both of them. Let's call it EB because it's called binormal direction. So EB is ET cross EN, all of them normal to each other with unit length. Let me redraw the same coordinate frame here. So I have, just to be sure what we are dealing with, this is ET, EN, and EB. So this is the frame that we are dealing with, not the frame that is also moving, just to make sure that it's only rotating, not moving with the location of the particle. So in this case, when we have this normal and tangential, vector R, actually you can define it however you want, really doesn't matter. It doesn't make sense in the normal tangential direction that much, so feel free to define it in however frame you want. The interesting one is V, the velocity vector. And this frame is useful because velocity is always tangential to the path. So that's why in the first place we look at this. And if we consider some reference point and the lengths of curve along that. Let's call it S. So V, we know it's always along always tangent to the path, so it is along ET, and the the magnitude of that is how fast we are moving along the length. So how fast this length length coordinate S is changing. So that is a very nice and compact way to define velocity. And acceleration A is derivative of that, V dot, which is S double dot ET plus S dot E dot T. Remember, ET is rotating. It is a little cumbersome, not cumbersome, but I can write it here. Omega is S dot tau, this is the torsion, ET plus S dot over rho, this is the curvature, EB. This is the rate of rotation of this frame, but let's forget about that. Let's look a little more intuitively into what this E dot T is. So as my particle moves from one point to another, so here is the path, and oh, that's not a good path. Let me, oh no. Let me change my color, green. This is good, that's my path. My particle goes from here to here. So originally this was ET, then it became that. Sorry for my kind of shaky drawing. And in this case, the normals always point to the center of the curvature. Let's pretend that this distance is small enough. So I have an arc, a very small arc centered around the center of curvature. As the particle moves, it traverses a distance ds, and the angle changes some amount d theta. And what I'm trying to find is how much this ET, this one is changing. So ET was originally like this, a little better. This was at the beginning. This was at the end. So this is the DET that I'm trying to find. Notice that this angle is the same as d theta, which is this same angle. This is d theta. So my DET is actually 1, the length of this, times the angle, d theta. And looking at this diagram, this d theta is the length of the arc, 1 ds over rho. So let's call it here ds equals rho, which is the radius of curvature, rho d theta. So DET is ds over rho, and I can divide it by some dt. What I get is E dot T is S dot over rho. You see, it shows up here. So what I have is S double dot ET plus S dot squared over rho. Oh, I didn't mention this. Okay, this is the norm of it actually. And the direction is along my normal. So in this case, et dot t is s dot over rho en. That is what it is. So multiplying that is going to be en. So s double dot is how fast we are accelerating along the path, and this s dot squared over rho is more or less the centripetal acceleration toward the center of the curve. So okay, that's all I think I have for now for this video. It was a little longer, but it's okay. I'll see you on the next video.